Our steel has an cast dendritic microstructure composed of cementite, and the phases are not evenly distributed throughout the cementite is very strong due to its high carbon content. It's mostly iron and very malleable. By heating the metal up past its austenitization point, we can easily distribute the carbon through the formation of austenite. By allowing the metal to cool in air, we can reform the grains and create a pearlite microstructure. While the carbon has returned to the cementite, we now have a homogenized microstructure of layered cementite and ferrite. Next, we want to redistribute the carbon, but ensure it stays distributed to maintain the increase in hardness. By heating past the austenitization point and not allowing the lattice to cool slowly, instead rapidly cool it, we can trap the carbon and form a martensite microstructure. This process imposes lots of stresses on the lattice, but increases its hardness, creating a strong but brittle metal. The final step would be to relax these stresses to ensure the blade doesn't shatter on it. Through tempering the steel, we can form tempered martens. The metal lost some hardness in exchange for ductility, creating a blade with far more toughness and hardness than the metal we started with.
I'm Lillian Beliveau, and I 3D modeled the blade guard and pommel using Maya to create a level of organic realism I felt necessary in emulating the original handcrafted design. While we went through many iterations of the pommel, researching and recreating different art styles of the era, we eventually decided to use a scan of a lion on the Purdue engineering fountain as a way of reclaiming a traditionally British symbol in addition to incorporating some school spirit. The original detailing on the blade guard was quite simple, so we wanted to elevate the flower in the center. This led me to research the flower garden at Mount Vernon, taking inspiration from the French striped marigolds in the upper garden, which I loosely blended together with the original design.
In order to cast the more detailed pieces, such as the floral guard and the lion's head, a technique called investment casting was used. The two pieces were 3D modeled and made into investment trees. They were then printed out of PLA, then dipped in suspended slurry and a silicone powder repeatedly in order to create a ceramic shell. Once the shell was sufficiently thick, in this case 10 or 11 layers, the PLA was burned out. Then bronze was poured into the molds. The ceramic shell was then cracked open to reveal the cast parts.
After rough face milling, our blacksmith Keenan took the sword, cut it down into shape, and warped it in order to give it the signature curve of the silver lion cutto. This year, we had the opportunity to work with Kimura Foundry America, a sandcasting foundry based out of Shelbyville, Indiana. Kimura Foundry America specializes in 3D printed sand molds. Those are advantageous for quick prototyping of steel parts and fast iterations on different patterns.
To begin the casting process, we modeled the casting tree inside of SolidWorks. The model consisted of the blade profile, vents, sprues, runners, and gates. After modifying the model up to version 5, we simulated it in Magma. After making many iterations and putting them through the fluid simulation, we arrived at our final version, version 8. This version was created in collaboration with our industry partner, Kimura Foundry. It included many risers very close to the blade profile so that they would fill the profile during shrinkage and help with porosity. After many weeks of attempting to cast successfully, we decided that due to time constraints and casting failures, we would not continue with this project, but it gave us valuable experience in creating a model, creating copes and drags, and collaborating with industry partners.